Yes, shall we start? Let me very briefly remind you of what we have done last week. We started from the QCD Lagrangian, the Lagrangian of the fundamental theory that someone perhaps was not very familiar with, but sum over f t slash minus mf psi. This is all the contains all the complexities that we have seen, and we have discovered that in a limit in which the quark, the lightest quarks become massless, and this is quite a well verified limit because values of these masses are about 2 MeV and about 6 MeV. So it is very small values compared to the hadronic scale. Then there is a symmetry, the chiral symmetry. This Lagrangian exhibits the chiral symmetry, SU to left times SU to right. And we have seen the consequences of this symmetry, the so-called chiral word identities, and a way, very synthetical way to resume all these consequences, all these word identities, through the use of the so-called generating functional of the connected green function, which depends on scalars, on sources, external sources, coupled to the quark bilinears. And this has the expression in terms of LQCD plus psi bar gamma mu v mu plus gamma 5 a mu minus s plus I gamma 5p psi. So these are the external sources. By taking derivatives with respect to these external sources, you compute the connected green function of the QCD. And all the word identities are relations among these different correlation functions. All these word identities are contained in a simple equation. The fact that this functional is invariant if we transform the source in the following way. Mu S P. Okay, there is also a remainder which corresponds to the chiral anomaly. This is well known. For simplicity, the important thing that it is a constraint, okay, where V prime and so on are the transformed sources, okay, transformed under the local chiral symmetry. Specifically, this okay, this transformation are the transformation by which the external, for instance, left current, okay, which is related to a combination of vector minus axial, okay, V mu minus A mu over 2, this is the left source, must transform in this way, like VL, L mu VL dagger minus I d mu VL dagger, okay? If we subject the left sources to this transformation, the right sources, which is the combination with the plus, vector plus axial, the axial source to the transformation with the SU to right group, R mu VR dagger minus E d mu VR dagger. And also we subject the scalar and pseudoscalar sources to this transformation. V R S plus IP VL dagger P VL S minus IP VR dagger then this functional is invariant. Okay, these equations contain all the consequences of chiral symmetry, of approximate chiral symmetry, because it is an approximate symmetry, but also of, of also contains the partial, let's say, conservation of current information. It is enough if we consider these scalar sources as expanded not around zero, but around the real value of the quark mass matrix. So in this expression, there are all these word identities for exact chiral symmetry and also approximate chiral symmetry. Okay. Then we have discussed the fate of this symmetry. The fact that the chiral symmetry is spontaneously broken to the vectorial subgroup of the chiral group, vectorial subgroup. And this has the consequence that, that there are Goldstone bosons, zero mass particles. And we have seen arguments that induced us to identify the pions as the Goldstone bosons of this spontaneous breakdown pions. There are three particles which are massless in the chiral limit. Okay. In fact, the pions are not massless. They have a mass of 100 MeV, more or less, which is much smaller than the hadronic scale, than the mass of any other hadron. Any other hadron whose mass is not protected, we say, by some symmetry, like the pions mass. Okay. Away from the chiral. So if the lightest quark were massless, exactly massless, then the quark mass would be zero, and they would be Goldstone bosons. Instead, they are almost Goldstone bosons. Sometimes people say pseudo Goldstone bosons. Okay, for zero mass particles, the mass is different from zero, and it is linear in the quark masses. Okay. The relation is the following: minus m up plus m down. And this is, okay, q bar q. Is expressed in terms of one of the order parameters of chiral symmetry breaking. The quark condensate is the simplest one. These relations is the so-called Gell-Mann-Ox-Renner relation. Okay. If quarks massless, then pions massless also. Away from the chiral limit, the mass is different from zero. Okay. Then also this fact, the fact that there is a mass gap, led us to look for a representation of that generating functional in terms of the lightest excitations. Because you see, in this quantum field theory, in the path integral formulations, is like fluctuating an average of, there is the analogy of the quantum field theory with the statistical mechanics. These fluctuations are mediated by the weighting factor, which depends on the action. So if there is a particle which is much lighter than all the other, then we are allowed to look for a low energy representation of this generating functional in terms not of fluctuating quark gluons and antiquarks, but in terms of fluctuating pions, okay, Goldstone bosons. The only one that are light enough to fluctuate, okay, because these fluctuations are weighted by the actions, and the actions goes with the mass of the particles. The higher the mass, the more suppressed these fluctuations in the statistical mechanics analogy. Here we have the action, which will be not the action of the fundamental theory, QCD, but the action of another theory, on an effective theory, whose degrees of freedoms are the pions. And the pions are collected in this matrix U. It is an SU2 matrix, as we have seen. We have identified the pions as the coordinates of the quotient group of this spontaneous breaking. So the U belongs to this quotient space SU2 right over SU2 vector. And with specific transformation laws under the chiral symmetry. If you remember, we have seen that this SU2 matrix, which collects the pion fields, okay, transforms under the chiral symmetry like that. VR, U, VL cross, okay? And a way to remember this is that the right transformation appears on the left, and the left transformation appears on the right. And this is the accident of the history, but history has to be respected. So everybody sticks to this counterintuitive notation. Okay. So, for instance, you see that now, where are the pions here? Where are the pions are coordinates of this SU2 group. Okay, U belongs to SU2. This quotient group is an SU2. You see, SU2 times SU2 divided by SU2 is SU2. Okay, and pions appears in different possibilities. Parameterize this SU2 matrix in different ways. The canonical choice is to express the SU2 matrix like that: pi A tau A over F. This is canonical choice. Tau A are the Pauli matrices, okay? And A is an index, isospin index, which runs from 1 to 3. But this is not the only. Of course, this matrix is unitary, okay? It's also spatial unitary, because these tau are traceless, okay? So it is an SU2 matrix. It's not the only possibility. There is also a so-called sigma model parametrization for this matrix U. So comma U could also be sigma plus I pi A tau A over F with the constraints sigma square minus pi over F square is equal to the number 1. Okay. With this, so you can substitute the sigma here and discover that this is an SU2 matrix. Also a good choice. So the pions enter in this expression for the matrix U in a very nonlinear way. So transformation law for the U matrix is linear, but transformation properties of the fields pi, which parameterize this matrix, is very nonlinear. So, and we start from there, from the fact that this transformation was non-linearly realized for the pions. And in one of the exercises in the notes, you have to write down the most general possible parametrization of this matrix U in terms of the pion fields pi A, with the constraints that pi A, of course, must transform like an isovector, must be a isotriplet, okay, is a triplet of isospin. Different choices of the pion fields, of the parametrization of these Goldstone bosons, amount to the same expression for the functional, because pi are simply, in this expression, dummy integration variables. So nothing depends on the choice. You can do reparametrization of the fields and obtain the same QCD correlation functions. No? These are not, so the correlation functions are independent of the choice of the pion fields, of the choice of the ingredients of these effective theories, okay? Of course, amplitudes involving pions in reality can be viewed as residues of the poles of these QCD Green functions. So these residues, which are the scattering matrix elements, are independent of the choice of parametrization of the pion fields. But away from these poles, as we say, off shell, these matrix elements of pion fields can depend on the parametrization, only on shell. Okay, these the observables are independent of the choice of the pion field. But if we change choice of the pion field, then we have to expect differences off shell. Okay. Now, so most of people use these canonical coordinates for the matrix U, but in any case, from this transformation law for the pion matrix, let's say, and the transformation which is written here, you see that this source S plus IP, okay, normally this combination is called chi, collect scalar and pseudo-scalar sources. And this other transformation is, of course, chi-dagger, okay? Instead of S and P, we can talk about chi and chi-dagger as independent external sources. So this source chi transforms in exactly the same way as the pion field matrix. So for instance, if we take the combination, the multiplication of these two 2x2 matrices, U dagger chi, this transforms in this way. Okay, U dagger transforms like VL, U dagger, VR dagger, and then chi, which transforms like VR chi, VL dagger. This is 1 because they are SU2 matrices. And so U cross chi transforms in a simple way. It is not an invariant. Okay, it's not an invariant. This is, I recall you that this is an SU2 matrix. Okay, sorry, this is a matrix. U dagger chi is a 2x2 matrix. U is a 2x2 matrix. Also the sources, okay, this V, A, S, and P are 2x2 objects. We have seen this last time. So these are all 2x2 matrices. If we take the flavor trace of these 2x2 matrices, okay, we obtain an object, a number, one number. And these numbers, by the cyclic property of the trace, you can remove to the left, this is invariant, U cross chi. So we have produced a candidate term which can appear in this effective Lagrangian, okay? Because it is invariant under the local chiral symmetry. And this invariance under local chiral symmetry ensures the properties of invariance of the generating functional. Also, the QCD was invariant with the addition of the external source under this local chiral symmetry, and that implied that relation among green functions. In an effective realization of that, we have to identify all possible interactions are invariant under the same symmetry. So one of those is this one, U cross dagger traced over flavor. This is a possible term in the effective Lagrangian. Well, the Lagrangian must be a real function. So we have to add the complex conjugate, and the structure which can appear actually is the following one. Trace of U cross chi plus chi cross U. Okay? This is only one possible terms. There can be many more. For instance, the square of this is also invariant. Or U dagger chi square and then traced is another invariant. There is a whole possibility of possible invariant terms which can appear in this effective Lagrangian. Okay. Then, however, these interactions, if we are in the chiral limit, are zero in the absence of scalar or pseudo-scalar sources. You see, these sources were only devices to compute the correlation functions. If we evaluate, okay, this functional in the absence of the sources, then this term would not contribute, okay. And anyhow, it is okay. They will contribute, for instance, for the scalar form factor of the pion or for the pseudoscalar. But in any case, we want to look for more terms. Okay, more terms. This term like this is, of course, also an invariant term, u cross u. In the same way as u cross chi was an invariant term, except that this is not an interaction among pions. This is just a unity, or better to say, the number 2, okay, trace of the identity matrix. So it's not possible to have, there are no interactions there, interactions among pions. We could think about something like that. D mu u cross, d mu u, derivative of u cross times derivative of u. But this is not invariant because the derivative of the pion field u under the chiral symmetry get some extra contribution because these derivatives can act on VR, or it can act on the matrix of the pions, or it can act on the matrix VL U d mu VL dagger. So you see, if there would be only these terms, we could play the same game and build invariants. But there are some there are some more complicated terms. In this situation, we can remedy to this situation by introducing covariant derivatives, d mu u. Covariant derivatives of the pion fields is the following thing: d mu u minus I r mu u plus I u L mu. As always, the right sources appears on the left and the left on the right. Okay, so we can verify how this object transforms under chiral symmetry. So this d mu u we just did above. Okay, we have to understand how does this combination of terms transforms under the chiral symmetries. So this goes like minus I r mu. Transformation of r mu is written in this blackboard, so which is not very visible. I hope it is for you. Vr r mu Vr dagger minus I d mu Vr dagger. So this is a transformation of r mu. And then there is the transformation of u. Transformation of u is Vr u VL dagger. Okay? Which gives, you see, something quite simple, because VR dagger VR is equal to unity, but also there is a minus sign d mu VR u VL dagger, Okay, so you see this term exactly compensates this one. And in the same way, the last term in the covariant derivatives plus I u left goes into I, transformation of the pion field VR u VL dagger, times transformation of the left source. Okay, transformation of the left source, which is VL L mu VL dagger minus I d mu VL dagger. Okay, and as before, there is a simple term VR u L mu VL dagger from the first term, and then there is a plus VR u VL dagger d mu VL dagger. Okay. We would like this extra term to compensate the last one, right? The last one. And this is indeed the case, because since VL dagger is equal to unity, then d mu VL dagger is 0. So d mu VL dagger is equal to minus VL d mu VL dagger. So here I can replace minus VL d mu VL dagger. So that the entire term is minus VR U. There is a compensation between VL dagger and VL, and then d mu VL dagger, which is exactly compensating the one above. So in the end, with this definition of covariant derivative, we obtain that it is covariant. It transforms covariantly, as the name suggests, into this one, VL dagger. Okay, so covariance means that it transforms in the same way as a U. This is the meaning of covariant derivatives. And then, if this term is not allowed by chiral symmetry, the one with the covariant derivatives is allowed by chiral symmetry. This is invariant term under the chiral symmetry. The mu U dagger, the mu U. Okay, traced over flavor. Okay, so this gives rise to the possibility. These are the so-called, the covariant things are the so-called building blocks of the effective Lagrangian. And we have to combine these building blocks to form invariants which all appear in this effective Lagrangian. These are the rules of the game. To include in the effective Lagrangian all possible terms allowed by chiral symmetry. Allowed by chiral symmetry. There is an infinity of terms. One may wonder about the utility of such thing, but I hope this will become clear after, in a few minutes. Let me discuss other two ingredients, other two building blocks of this effective Lagrangian. These building blocks can be obtained by, let's say, like the field strength of the external sources. Okay, something like that, like the curvature, for instance. And this is d mu r nu minus d nu r mu minus I r mu r nu. Okay, these are matrices, R mu with two indices, like F mu nu, matrices with two indices, built in this way. Of course, being matrices, they don't commute, so this commutator is not zero. And you know how the right source transforms under chiral symmetry. It is written in the other blackboard. And so you can play this game and discover that this curvature transforms covariantly, in the sense that it transforms like that. R mu nu V R dagger. Okay? So for instance, a possible invariant term would be R mu nu. This is a possibility of term which appear here. Okay? But also the same can be done with the left sources, minus d nu L mu minus I commutator L mu L nu. Also these transforms, as you can imagine, L mu nu V L dagger. Okay, so you can have another term with this left curvature, L mu nu square. But also you can have, you see, these are terms quite, for most cases useless because they do not contain the pions. They only contain the sources. There are no pions. But you can build a combination of this. For instance, you can build combination of this right and left curvature. For instance, this thing, if you multiply by u and then L mu nu u dagger. Okay, this is a possible invariant term, you see, because R mu nu goes to VR R mu nu VR dagger. Then U goes like that, VR U VL dagger. Then this goes to VL L mu nu VL dagger, and then VL U dagger VR dagger. So all these combinations are 1, 1, 1. The other combination by the cyclic property of the trace can be put in the same on the same side. So we end up with U L mu nu U dagger. Okay, so this is a possible invariant term of the effect, and this contains the pions. So it is interaction of pions with the external sources. If you are interested in the left-right 2-point functions of QCD, this term will contribute. Okay, will contribute. Now, what is the utility of this infinity of terms? The utility lies in the fact that they contain more and more derivatives. More and more derivatives. There is a power counting rule on the top of this general construction. Okay, the power counting rule is the fact that each time there is a derivatives, okay, these correspond to momenta of the relevant particles or of the pions, let's say, okay, which at low energy they are small. Okay, so we say that each space-time derivatives bring some factor of the pion fields, of derivative of the pion fields, brings down the energy or the three momenta of the particles, which are both small quantities. Okay, so we say that these things are of order P, okay, where P generically denotes the soft momenta. Okay. Also, you see, since the derivative is combined with the sources in the covariant Lagrangian, also the sources R mu, L mu must go like order P. Okay, these are the rules of the game. For instance, this term R mu nu with these rules, it is of order P square because there is a derivative, and there is one external source, so order P square. Or in this contribution there is no derivatives, but there are two sources, so order P each. It makes order P square. Okay, so a term like this, for instance, it has to be counted as order P to the 4. Okay, why? Because this is order P square, no derivatives on U, so, and other two orders from L mu nu. So this is order P square, while the term written here is of order P square, you see? So we can expect it to be larger than the contributions that we have discussed before, larger. What about this term? This term, it contains no derivative, okay, because there is no derivatives. There is the external source chi, okay, chi. Now chi also there is a rule for chi. This is to be counted as order P square, P square. And why it is so? Because this chi is the scalar plus the pseudoscalar source. And at the end of our calculation, if we want to stay away from the chiral limit, in the chiral limit, this source, in the absence of scalar, pseudoscalar sources, this chi is simply 0. But away from the chiral limit, this S must be substituted for the quark mass matrix. So it is a 2 by 2 matrix having the quark masses in the diagonal. Okay, and so you see that these quark masses, m up or m down, are small quantities. We started from this. They are small quantities. They have to be counted like order p square. Why? Because of the relation that I have written here. Okay, because this m pi square is order p square. After all, it is the square of the 4 momenta of the pions. So if this 4 momenta is small, then this is order p square. So by consistency, the quark masses, and therefore the scalar, pseudoscalar sources, must be counted as order p square. Okay? So as a consequence, this term is of order p square on the same ground as this one. Okay? Now there is an important point. There are no terms with, let's say, dimension or soft dimension with chiral index, let's say, this 2, 4, and so on. It's kind of less than 2. There are no terms with chiral index less than 2. The most simple terms that we can write are these two of lowest dimension, of lowest chiral index. No possible terms with chiral index 0. This would be 1, u cross u, order p0, okay, order 1. But it is not an interaction term. It is simple the number 2, okay? So, and this is express the fact that the pion interactions are derivative ones. Each time a pion interacts with something, it does so according to its momentum. Okay? Pion couplings are derivative ones. And this is also contained in the Goldstone theory that I was mentioning before, the last lectures. Okay? Consequence of the Goldstone theory is that the pions are light, let's say massless, and that they interact weakly at low energies. And we recover these properties here. Okay? That there is no interaction term with dimension less than 2. So the Lagrangian can be ordered, all these effective Lagrangian, which does not appear anymore, but it can be ordered in this counting. So there will be a Lagrangian with order second order in this chiral index. There are only two possibilities, okay? Only these two structures in the lowest order effective Lagrangian. Only these two structures. What are these two numbers which appear here? F and B0. Well, F, we have already met this number. F was the scale of the pion fields. For instance, it appeared in this expression. Okay, it sets the scale of chiral symmetry breaking. It is a dimensionful parameter, F. It is included here with this square and over 4, so that the kinetic terms for the pions are of the standard type. Okay, this is the reason to insert this factor f squared over 4 there. Okay, notice that this Lagrangian contains infinitely many interaction terms. It describes vertices with 2 pions participating, like this, the kinetic term. It describes also terms with 4 pion participating, 6 pion participating, 8 pion participating. Number of pions is always even. This corresponds to the G parity, but we don't have time to discuss this. Okay, so this lowest order Lagrangian already contains interactions. For instance, it can describe pion-pion scattering, okay, because there are vertices here with 4 pion fields. So I have explained why there is this factor f squared in front of everything, because so that the kinetic term of the pions is canonically normalized. And then there is another number here, bit 0. Well, the combination f squared bit 0. These numbers, these constants, they are called low energy constants. LECs, low energy constant. They are the numbers which parameterize our ignorance about the low energy theory. Okay, so if we knew how to solve the QCD, then as it was the case for the example that we have seen of photon interactions, the Euler-Heisenberg effective Lagrangian of photon interactions. In that case, we can do calculation which brings from QED to the low energy Euler-Heisenberg Lagrangian, because QED is perturbative. But for QCD, this is not the case. So this translation is not possible in practice. But in principle, these low energy constants are QCD quantities. So they could be computed in the fundamental theory. Okay? Otherwise, the other possibility is to take them from the data, on processes involving pions. Because as I was saying, this Lagrangian contains interactions. Okay. How to pass, perhaps this is not clear, from this expression to this expression. You have to expand. Okay, you have to expand these U matrices like in powers of the pion field, pi a tau a over f plus I squared over 2 pi a pi b over f squared tau a tau b plus and so on. There is a whole tower of terms involving more and more pions, okay, of which you have to take these derivatives, multiplying with another tower of infinite interaction, and take the trace, okay, trace of the tau matrices you know how to do, and then you end up with interaction terms involving more and more pions, okay, more and more pions, but it's still the lowest order Lagrangian, the L2 Lagrangian, okay. So this simple Lagrangian is describing a lot of processes. It's not like the starting point of a perturbation theory in which, let's say, the kinetic terms describe the free theory. This is not a free theory. The pions interact, okay, but interact through the simplest interactions that we can write, okay. This Lagrangian, okay, if you are curious, then there are the next level in this hierarchy of Lagrangians is of order 4, p to the 4. One example is the one that was written before, and but now I don't know the mu u cross square plus. Okay, there are terms involving the square of the terms above with some coefficient, which is also a lower. I don't guarantee here about the real. I should consult the notes, but in the notes it will be written with the right factors. Then there is a factor like L3, and then u cross chi plus chi cross u square. Then there is a term L for d mu u dagger d mu chi plus d mu chi dagger d mu u plus, okay, the one that we have written, L5, I believe, R mu nu u al mu nu u dagger. Okay. There is also other term, H1 R mu nu, that we have encountered in this discussion, plus H2 L mu nu L mu nu. Okay. The rules of the game is to write down all possible independent terms, okay, which scale as the 4th power of this soft momentum. Okay. This L, L1, L2, L3, L5, there are six independent terms, L6. They are called low energy constants. They are the sub-leading versions of these ones, of these two ones. Okay, and this the notation L stands for low energy constants, small l. Instead, there are other constants which are called historical, and these are papers by Gasser-Lottwiller in the 80s, 1984, 1985. H1 and H2 are those terms which do not involve the pions. You remember we have discussed before. H stands for high, like high energy constants, because they are needed for other purposes than not for calculating processes involving pions. So, but the rules of the games are to compile all possible invariant terms. Of course, as long as you proceed in this expansion, you can produce a large number of possible invariant terms. The more you allow the appearance of derivatives, the more combinations of terms you can have. And so the 2 terms at leading order become 6 terms at next to leading order. And the next order, which would be L6, okay, would contain of the order of 100 almost terms, and so on. Okay. But if you are happy with small accuracy, okay, if you are happy with let's say with the gross features of the theory, if you limit yourself to the leading order Lagrange, and then you only have 2 constants, so a huge predicted power with only 2 constants taken from experiment once, then you can predict all other processes. Okay, so I think that now wanted to discuss very briefly the concept of renormalization, also because this was one of the questions that I have seen in the list of questions in to Professor Meng, that unfortunately I could not attend. So, but let's do that after the break. Okay. We resume at how much? 5 minutes? 10 minutes? Is it enough? 5 minutes? Or you want 10? I wanted to discuss very briefly the renormalization. As I was saying, this Lagrangian, the lowest order Lagrangian, already contains an infinite number of couplings. The first one is this terms is simply the kinetic terms of the pions. Okay, there will be also like m pi square pi a. This is the mass term, and this mass term is related with this low energy constant B0 and to the source chi, through the source to the source chi through the quark masses. So, and we have the Gell-Mann-Oxen relation that we had written before. But also, these are not interactions, simply the kinetic terms of the pions. There are only 2 fields participating, free theory. But there are also interactions, like interaction expanding this matrix U in powers of the pion fields. You get interactions like that. I don't know, there will be, now I don't want to make pi 4 and so on. There is a whole bunch of terms with more and more pions participating. For instance, coming from exactly this term, don't trust the coefficients here, just want to send the message. Okay, for instance, this will contribute to the pion-pion scattering. Okay, with 4 pion participating like that with 2 derivatives. So these terms will give a contribution to the pion-pion scattering depending on 2 powers of the pion momenta in different combination. Okay, which okay, but this term already, this is non-renormalizable in the usual sense. Why? What is the condition for renormalization in the field theory? Simply counting canonical dimension. What is the canonical dimension of a scalar field? 1. 1, this is order 6, much more than 4. So it is not renormalizable. All the terms, these terms are not renormalizable terms. But yes, please. Yes, you're right. So in addition to this, to the pi scattering, there will be an interaction like that. Okay, when the pions rescatter. Okay, the pion rescatter, and these intermediate states, you have to sum over a complete set of intermediate states. Okay, so you have a loop. Okay, this loop has an expression d for k. So if there is a particle pion with a momentum p1 entering and p2 entering, then, so to say, the intermediate momentum of these pions propagating is not fixed, can be whatever it likes. So let us call this k. Okay, so this one will be k minus p1 plus p2 because of momentum conservation. Okay, so in this loop you have 2 pion propagators. You can also do the same with the time-ordered perturbation theory, but also with covariant perturbation theory, like for Feynman diagrams. So this loop is something like that. There is integration over intermediate for momentum, and then there are 2 propagators, 2 pion propagators. One with momentum k squared minus m pi squared plus I epsilon. This is this propagator, and the other one with another k momentum to square minus m pi square plus E epsilon. You see? So, and this integral, you have to, this momentum can be whatever, okay? They can be arbitrarily large in principle. So you have a logarithmic divergence because you have d for k over k4 dimensionally, okay? So here you have like k cubed dk in hyperspherical coordinates, k cubed dk, divided by k4. So this for I energy is logarithmically divergent. So if you limit your integration to some cutoff lambda, this will be like a logarithm of lambda over some scale p1 or m pi. Okay, so it means that the perturbation theory, the consideration of more and more loops, complicated loops, leads to divergences. Okay, and divergences must be in the normalizable theory. This divergence can be disposed of by changing the coupling constants. For instance, in QED, you also have divergent loops. But you can say that, okay, the electric charge that I had written in the Lagrangian was not the real electric charge, it was just a parameter, which is also divergent. And its contribution, together with the contribution from these loops is finite. Okay, so this mechanism. So the theory is renormalizable when you have enough constants, okay, to absorb these divergences. This means in QED this is the case. Okay, I don't want to enter into too many details, but there is a simple rule to realize if one theory is renormalizable or not. This is if the canonical dimension of the interaction that you write is less than 4, less than or equal than 4. Okay, so in this case, where canonical dimension is dimensionality of these fields, which is 1, okay, 1 plus 1 is dimension 6, not renormalizable. The more more complicated loops you construct with these interactions, the more severe will be the divergences, and you don't have enough constants to absorb these divergences. Okay. But this only in the low energy, in the lowest order Lagrangian. Remember that the effective Lagrangian will contain all possible interactions. So yes, you have enough coupling constants in this theory, an infinity of coupling constants to absorb these divergences. Okay, so the effective theory is not, in some sense, it is renormalizable. Okay, simply the low energy the constants, the coupling constants that you have to renormalize are infinity in number. Okay, so this was realized by people in the 70s. Okay, that actually there was important thing is so-called order by order renormalization. Order by order renormalization. Let me also state that any diagrams, like for instance, we have written this, but you can do, for instance, this is a more complicated diagrams with the vertices from this Lagrangian, okay, which contributes to pion-pion scattering, for example, okay. It is a 1, 2, 3 loop diagrams. We will not have only one integration over k, but 3 integration over k. So for a diagrams with L loop, okay, if we count the number of powers of momenta k, okay, this will have 4 times the number of loops. Like here it was, because there is a d4 over d4k, so 4 times the number of loops. Then the powers of k will be diminished by twice the number of propagators of internal lines. You see here, for instance, each propagator is 1 over k squared. So in this counting, it counts like -2 each. In this case, -4. So minus twice. And then if we want to count the number of soft momenta, you will have to remember that in some of these vertices, there can be derivatives, okay? There can be derivatives. These also contribute powers of k. So here we have a further contribution from all the vertices. Let us call these vertices I, 1, 2, 3, 4 in this case, okay? Number of vertices of I type times the number of derivatives appearing in this, okay, I type vertex. And there is also, for any diagrams, there is a relation which relates, a topological relation, which relates number of loops in any given diagram, number of internal line in any given diagram, and total number of vertices. I never remember, but let us try. L is equal to V minus I plus 1. In this case, I minus V plus 1. In this example, number of internal lines is 1, 2, 3, 4, 6, 7. 7. Number of vertices is 4. What? Please? 6, what was 6? Number? Yes, if this 7 is 7, 6 minus 4 plus 1, it is 3. Okay, so it is this way around. This is a general topological idea. You can cut a line adding a vertex and you realize by induction that you can prove this identity. L equal I minus V plus 1. Okay, so instead of I here, we can express, you can use this relation. So I is equal to number of loops plus number of vertices minus 1. So this chiral power nu is equal to 4 times L minus twice L minus twice V minus and plus 2 plus this sum over all the vertices. And then you see that you can do like that. 2L plus 2 plus sum over number of vertices of types I minus 2. See? Because the number of vertices is simply the total number of vertices of any type. So any diagram with L loop, okay, will have a chiral power, this soft index, expressed by this relation. If it has n1 vertices of type 1, for instance, this type, n2 vertices of type 2, okay, for instance, this vertex, okay, you classify all possible kind of vertex that you can have, and then they contribute in this way. Now there is a fact that there are no vertices, any vertices, which have this di smaller than 2. For any vertex, this di is at least 2, like in our case. And this is a manifestation of the fact that pions couple derivatively. You could say, okay, here there are no derivatives, but there are the source chi or quark masses. Okay? They count like 2 powers. So this is a number which is never negative. So the more complicated the diagram, the more loops you add, the more is the chiral power of this diagram. Okay, and in this case, the chiral power, if the vertices are all from the leading order Lagrangian with this di equal to 2, this is 0. So the chiral power of these loops is simply 2L plus 2. In this case, it is, well, 3 loops times 2, 6, 8. So this is order p to the 8. Okay, p to the 8. So in order to find a low energy constant which would absorb the divergence coming from this loop, we should consider the Lagrangian not L2, L4, L6, but coming from L8. Okay, there will be terms in the Lagrangian from L8, which I think is not known. Okay, nobody has classified the Lagrangian at order 8, but one of the terms could be like that: u cross d mu u to the power 4. Okay, this is one of thousands, I believe, of possibilities of terms at order p to the 8. Okay, and this term will contribute to pion-pion scattering. Okay, with a dimension with 8 powers of momentum. Okay, so like this. Okay, so it has the potentiality to absorb the divergence. So in the effective theory, it's not true that the theory is not normalizable. It is normalizable order by order in this low energy expansion. I say with other words, if we decide that we ignore all but the leading order, okay, then a divergence arising at order P4 by power counting, we are legitimate to ignore. If we are more ambitious and we want to consider a more sophisticated theory, not only the leading order Lagrangian, but also the next to leading order Lagrangian, L4, then we can decide that all divergences arising at order more than P4 are simply ignored. For instance, these three loops diagrams would not be part of the theory at next to leading order, at order P to the 4. Okay, so the theory is order by order normalizable, provided one decides to ignore all contribution coming from involving more powers of momenta. Okay, so this is the meaning of renormalization in the effective theory sense. It's not it is not true that theory is not renormalizable. It is renormalizable because all divergences can be removed, provided you consider the whole infinity of possible terms. Okay, if you stick to a given accuracy, for instance, order P to the 4, then you are only allowed to consider one loop diagram. In the description of things at order P to the 4, L is limited to 1, because this number is never negative. So at most, you have to consider one loop diagram. In the Goldstone boson theory, the calculations up to now have been computed at two-loop level, so at order P to the 6. So, and this is quite enough to get very accurate result in the Goldstone boson sector. I want now to discuss the role of nucleons at this point. The extension of this argument to nucleons. I also wanted to discuss the role of but I don't have time for this, the role of the resonances, the so-called resonance saturation of the low energy constants. Perhaps I will put this argument in the notes, and let me discuss the extension of this framework to the nucleons, because up to now there are only pions. So the nucleons N are a doublet of isospin, Pn, doublet of isospin. What does it mean, a doublet of isospin? That under vector transformation, SU2 vector transformation, it transforms with the Pauli matrices. But so under SU2 vectorial transforms under V. SU2 it means VL equal VR equal V. Okay, so this is the constraint. The nucleons are isodoublets, but we have to ask transformation properties not only under the isospin group, but under the chiral group, the whole chiral group. And in principle, the thing is that we are free to choose any representation that any rule for the nucleons transformation as we wish. Let me explain why. For instance, a very natural transformation is the following, that the left chirality component of the nucleon doublet transforms with the transformation of SU2 left, and the right-handed component of the nucleon isodoublet transforms like the right transformation. You see, this left component, I remind you that these are simply the projection on the right and left chirality of nucleons. Okay, so you have understand a little bit of what is not written here. N here is a 2 vector in isospin space, but there are more spaces in this game, no? Because there are also proton and neutron are Dirac fields, okay? So they carry Dirac indices on which this gamma 5, like the quarks, for instance, nucleons are fermions like the quarks, so they carry Dirac indices on which these gamma 5 transformations act, okay? So and so we could decide that the nucleons, for instance, transform under the chiral transformation like the quarks, the quark doublet, up and down. Okay. Or notice that in the limit of the vectorial symmetry, when the left chirality transformation and right chirality transformation are the same, this respects the rule of isospin transformation. So it qualifies the nucleons as isodoublet, this transformation. But it's not the only possibility. One could say that, for instance, N possibility B, for instance, the fact that N transform like the right transformation. Both left and right chirality of the nucleon fields can be taken to transform according to the right transformation. Of course, also this possibility satisfies the constraint that under a vectorial group VL equal VR equal V, this is the transformation. But there is also another possibility, among many others, that the nucleon field transformed according to the left transformation. Okay? So, how it is possible that we have the freedom to choose the representation for the nucleon fields? Suppose that we decide that the nucleon field transforms in this way under a chiral transformation. So somehow the nucleons only fill the left part of the chiral group. Okay? Then we can define another field n prime simply multiplying the nucleon doublet Pn, proton neutron, with an SU2 transformation, which is the pion, the Goldson boson matrix U. Okay, let's see how this new primed field, this redefinition of the nucleon field, transforms under the chiral symmetry. We know how the Goldson boson transform. It is written there. Well, not anymore, but it transforms with the right transformation to the left. Then one, remember always, VL dagger. This is the transformation of U, and then the transformation of N in this C case. Transformation of N is simply VL times N. Now remember that VL is a SU2 transformation, so this is the identity matrix. And you see that this transforms like VR times UN. Then VR times what I have called N prime. So we started from an assignment of transformation under the chiral group for the nucleon field of type C. I transform the nucleon fields by dressing it with the Goldstone bosons in this way, and I end up with another prescription that this N prime field transform according to the option B. Okay, so the Goldstone boson can be taken to relate all these possible choices for the nucleon fields. Okay, and the field that we choose does not matter, like we commented before for the pions. The choice of the nucleon fields is a matter of convenience, will not change on-shell matrix element involving nucleons. It will affect off-shell behavior, but will not change the on-shell matrix element. So we are free, okay? For instance, but there is one choice which is more convenient than all the others. And in order to discuss this, let me write down one possible. For instance, let us choose option A, the most natural one, the parity invariant one, A, and build the following mass term for the nucleons. You remember mass term, left and right chirality. Okay, so we can do like that. But with option A, this is not chiral invariant because R transforms with the NR, right chirality with VR, left chirality with VL, which do not compensate each other. But if I insert here the Goldstone matrix U, then this is a invariant number. And if I insert here U dagger, then this is an invariant. Okay, this is an invariant term. So this can enter in the effective Lagrangian of nucleons and pions, so describing interaction of pion and nucleons, provided I choose the option A for the transformation of the nucleon field. It is not very nice because these terms are not of derivative type. You remember that quite crucial in the argument for this perturbative organization of the effective theory was the fact that pion interacted derivatively. Here, pions are interacting with the nucleons non-derivatively, and this will spoil all the counting. Okay, so this will, okay, so it's not the good option, this option number A. Somehow, okay, so this, but this can be remedied in the following way. For instance, consider this term, n bar r. The trick is to consider the square root of this matrix, SU2 matrix U, okay? So it is another nonlinearity. And assign this, okay, call, if you like, this field n prime L, and this field n prime bar R, okay? In order to dispose of the non-derivative pion interaction. Let me state it more clearly. First of all, I recall you that this amounts to n prime L equal U n L, and n prime right equal U dagger n right, where small u is the square root of capital U that we talked about, and the dagger is the dagger. So in this way, this is simply a mass term with no pion, so it makes no harm because it's not a non-derivative. A non-derivative, okay? So, and we introduce a matrix, an SU2 matrix H, which enter in the transformation of U in this way. U VL dagger and equal to VR U H dagger. if we do that, we see that u square which was the capital U transform like VR U H dagger H U VL dagger, and this is unity. So we recover VR U VL dagger, the right transformation properties of U. Okay, and the dagger of U is simply goes into the Hermitian conjugate, so transform like that, VL U dagger H dagger, which is equal to H U dagger VR dagger. So perhaps you wonder what this matrix H is, but it is written actually in this equation because U goes into the transformed U that we expressed like this, U VL dagger, okay, transform like that. And we know that therefore H, if you right multiply by VL and then you right multiply by U cross, you obtain that H is equal to U prime VL U cross. Okay, so this H is a quite complicated function which takes this form. So it is square root of VR U VL dagger VL square root of U dagger. Okay, if you are curious about this matrix H, it is this quite ugly expression. Okay, just to say that it is known what is this matrix H, that we didn't make like the 3 cards game. Okay, so this is. And now we can ask about transformation of the fields n prime. Okay, how do the new fields defined in this way by dressing them with this, not the entire U, but the square root of U. Okay, then we discover this thing that n prime, which n prime left, which was U times n left, goes under the chiral symmetry into the arrival point, let's say, of small u, and we rewrite this expression, HU, and then there is VL dagger, okay, and then the arrival point of NL. It is my mistake that I have erased the assumption that we were making, assumption A, our starting point. Okay, this parity conserving possibility. So we know how does left nucleon transforms. Transform like VL and L. And now there is this fortunate circumstance that it is identity matrix. So we end up with U n left, which is H, this famous H that we discussed, times NL prime. So the moral is that the new defined fields, this dressed left chirality fields, transforms with this matrix H, okay, like that. And what about the dressed right nucleon fields, NR, which is defined with U cross? It transforms like the transformation of U dagger. Transformation of U dagger, I choose the second possibility so that we have the matrix H entering, H, U dagger, and then VR dagger. This is the transformation of U dagger. Then we have to transform the right-handed field in this way, VR and right, and we are happy again because this is the identity. So we have H, U dagger, N R. So H, N prime. So in this way, both chirality, left and right chiralities of the nucleon doublet transform like that. Okay, transform in this way, in this complicated way. And now it is an exercise that I leave you to show that this realizes representation of the, I mean, that this transformation rule satisfy the group composition rule. Okay, group composition rule. So the if U goes to VR U VL dagger with H defined in this ugly way. So please show that by combining two different chiral transformation with VR1 and VL1 and VR2, VL2, by combining them, okay, one after the other, you respect the group composition law. It doesn't seem very trivial from this expression of H, but it is the case. And so we have disposed of the non-derivative pion interaction in this case, and but we can have derivative interactions. And let's see what type of derivative interactions. Let me erase this thing. So from now on, we will stick to this choice, not A, not B, not C, for the transformation properties of the nucleon fields, but this one. Okay? So that the nucleon field transform with this matrix H. This is SU2 matrix H. This matrix H in the literature is known as the compensating field. Compensating field. H, compensating field. You see, we cannot, for instance, combine pions and nucleons to interact themselves with terms like that. For instance, we could say like that to respect the Lorentz symmetry. This is one possibility, but it is not chiral invariant because this, we know, it is a covariant derivative, so it transforms like a pion field itself. But instead, this transforms like H, and this transforms like H dagger. So it does not compensate. Okay. So the solution is to add so this is not the right choice, but if we multiply by small u dagger, okay, this means that I'm over time or not? I'm okay. So just let me convince you that this is so we are what we do is to define another building block u cross, and you can show that by exercise that this under chiral transformation goes to H u mu H bar. Okay, H u mu H bar. It is not hard. You know how U dagger transform. You know how capital U transform. And then the combination transforms like that. So now you see that you can have invariant term like that. Gamma mu, U mu, N. And in order to respect parity, you have also to insert gamma 5 because pions are pseudoscalar. So this is a possible interaction term of pions and nucleon, chiral invariant interaction term. It has a low energy constant, which is nothing else than GA 1.27. This is measured in the neutron beta decay. Okay, so this is one of the terms in the effective Lagrangian of pion and nucleons. The best thing is that I recover this from this point tomorrow and leave space if there are questions, despite the tiredness. I also would like to ask you to collect the questions like you did with Professor Meng, no? Because tomorrow afternoon, the last, let's say, the extra will be devoted to your questions. So please collect the question. The more interest in the question, the less the chance that I can answer. But this should not stop you from asking interesting questions. If you send me your questions in advance, there are more chances that I will be able to give a more thought answer. Otherwise, you take the risk